Here we go. 4.6 is going to be our last section for unit 4. And we're going over rational functions and their models. Basically, anytime you hear the word models, you should think real world. So we're just going to make sure at this point you can identify the domain and the range, tell me where the asymptotes are, and graph the functions accordingly. So rational function, what makes something a rational function is that you have a polynomial in the numerator and a polynomial in the denominator. Does that make sense? You're gonna have one and the other. Well, I'm confusing you guys with pre-cal. We haven't did that. Pre-cal. My real pre-cal, we did that. Yeah. That's in real pre-cal. Right? I was like, wait, I just realized. And then I looked at Anna and I was like, wait, no, wrong class. What? I was like, oh, we've already learned this, but I was talking about pre-cal. Had already learned. Yes, pre-cal's already learned this. All right, you guys have not correction. Correct. This pre-cal class has not learned this yet. Okay, but rational function. So again, a rational function is when you have a polynomial in the numerator and in the denominator. The key point is in the denominator when you have a variable in the denominator. So we're going to talk about identifying their domain, and identifying asymptotes, interpreting the asymptotes, and graphing. Okay, it's like really fast, FYI. So what we're going to be looking for are points of discontinuity, things that cause our function to break. Okay, there are 3 types of discontinuity. We have gaps or joints, gaps, holes, and asymptotes. Okay, gaps, holes, and asymptotes. These are things that causes problems in my function. All right. Oh, you see nothing. You see nothing. All right, here we go. So it says determine if the function is rational and state its domain. Okay. This function is rational because we have a variable in the denominator. Does that make sense? So this is a rational function because there is a variable in the denominator. Yes? That's what makes it a rational. Because there's a variable in the denominator, that means that there's limits on our denominator. Okay? It is okay for 0 to be in the numerator, but it is a no-go for 0 to be in the denominator. Okay? I know I said that in algebra 2. Don't say I didn't. Yeah. It is okay in the numerator, but a no-go in the denominator. So that means that our denominator cannot equal 0. Does that make sense? And that's going to help us find our domain restrictions. So your denominator cannot equal 0. At the x values that make it equal to 0, those are our domain restrictions. That is what we're saying x cannot be. Because otherwise, x can be anything, right? But once we set this limit, this is what x cannot be, okay? So I'm going to take my domain, my denominator, and set it equal to 0. So 1 minus x squared equal to 0. What would make this equal to 0? If you don't know, then you solve for x. So I'm going to subtract 1. That's going to leave with negative x squared equals negative 1. I'm going to divide by negative 1. That's going to leave me with x squared equals positive 1. I'm going to take the square root. That gives me x equals positive 1 and negative 1. But logically, you should have been able to look at this and tell me that x couldn't be 1. I was hoping for that. But mathematically, do we see what x cannot be? Okay, x cannot be negative 1 or 1. Because if I plug those in, it would make my denominator equal to 0. Okay, so it says, determine if rational function. Yes, it is rational. And because it's rational, here's my domain. There are 2 ways to write our domain. Okay, the first way we're going to talk about is interval notation. Interval notation is saying that what is your domain as you go from left to right across, right? If I'm going forever to the left, my interval starts at negative infinity. I'm working my way up into my first restriction. My first restriction is at negative 1. Then I restart, and I'm working my way from negative 1 to my next restriction, which is at positive 1. And then I continue forever to the right. This is my interval notation of my domain. My simple inequality notation is just that x cannot equal 1 and x cannot equal -1. That's what this is telling me. And the reason being is that this is where it will make my denominator equal to 0. It can be any x can be whatever else it wants to be, but it just cannot be 1 and -1. Okay, that's the limit that's on this function. Yes. All right. Next one, determine if the function is rational and state its domain. Okay, so the first thing you want to check for is that there's a variable in the denominator. Yes, there is a variable in the denominator. However, it's not rational. And the reason why it's not rational is because of this root. Okay, this guy right here makes me not rational. Okay, and it's actually a mixture of a function, but it's not a rational function. In order to be a rational function, your powers have, it's not rational, have to be positive integers. So the powers of your variables have to be positive integers. And this right here is not a positive integer. This is actually x to the 1/3. And is 1/3 an integer? No, it is not. It is just a number. Can't even think, but it's not an integer. Did you need me?
Oh, did I leave the charger?
IDK.
Yeah.
Okay, now, even though it's not rational, and the domain here, notice that if I take this and set it equal to 0, it's not going to be anything that's going to restrict it. So if I have x squared plus 4 equal to 0, is there anything that I can plug into this that's going to make it equal to 0? No, because what happens to a negative when you square it? It becomes a positive. So there's no way for me to make a -4. Does that make sense? So this can never happen. So x squared plus 4 can never equal 0 on its own. So therefore, the domain is all real numbers. It's from -infinity to +infinity. There are no restrictions. There's nothing stopping me for this function to go on and be its weird shape. If it hadn't been squared, would I have a domain restriction? It could be -4, right? But because of that square, it prevents it from saying I can cancel out and equal 0. Okay, so the answer is no, it's not rational. But here is the domain. And the domain goes forever to the left and forever to the right. Now, what the shape is doing is on its own. So in example A, we saw an example of a rational function with a domain restriction. Example B, we saw a non-rational example, but still in a domain with no restrictions. Yes, do we see the difference? This one had restrictions because I could make the denominator equal to 0, right? This one had no restrictions because there's no way for me to make that denominator equal to 0. Hopefully that's clicking. All right, next is when are rational functions modeled in the real world? Well, here is an example. Suppose that a construction zone can allow 50 cars per hour to pass through, that the cars arrive randomly at a rate of X cars per hour. Then the average number of cars waiting in line to get through the construction zone can be estimated by n of x equals x squared divided by 2500 minus 50x. Okay. And it says, can you evaluate? Well, just because it's rational, do we evaluate any differently? No. What does evaluate mean for us to do? Plug in, plug it in, plug it in. Anytime you evaluate, you should think of plugging it in. So it's asking, can I substitute and find what it would be at 20, 40, 49? Is that doable? Yes. Okay. So, and I'm going to pull up the calculator and do it. All right, I'm gonna show y'all a little nifty trick. Clear my handy dandy calculator. Second, plus 7, 1, 2. I'm gonna go to y equals. I'm gonna protect my numerator, so I have x squared.
We'll have to do that, right?
Because I don't have the fraction bar. Yes. I mean, you could do it with me if you want. Alpha and the variable key. All right. So there is my function. And I want to find n of 20, n of 40, and n of 49. I'm going to go to my table setting. And I'm going to switch it from auto to ask. Because do I want to scroll all the way down to 20, all the way down to 40? No, I do not. And now this allows me, when I go to my table, I'm going to type in what I'm looking for. I need 20, I need 40, and I need 49. Any questions about inputting and turning on the ask? Yes. So to turn on the ask, it's second window, and you go from independent, your independent variable from I can't talk, from auto to ask. And then now when you go to your table, it allows you to put in the values that you need. Okay. So
2,500? Oh, 50.
it says x squared divided by 2,500 minus 50x.
How do you make it this?
So because you guys use your fraction bar, it's going to automatically give you a fraction. Unless, I think if you change your mode and you force it to round. So if you go to your mode and you force it to round, it should do it. Yeah. Okay. So we have 20, 40, 49. And it's saying, in terms of this problem, what are these telling me? What is the n telling me? N is the what? The number of cars waiting. So n is our number of cars waiting. So if I have 20 is moving 20 cars per hour. So if they're moving 20 cars per hour, the number of cars waiting is basically no cars, right? If they're moving 40 cars per hour, how many cars are waiting? 3. Again, in this case, I probably don't need decimals because it's cars and you can't have a fraction of a car, right? So when I go back to my table, you can see it better, right? So if I'm moving at 20 cars per hour, I'm going to have a no. When we are moving at 40, we have 3 cars. When we're moving at 49, we have 48 cars. And so that's what that value is telling you. Now it says, what happens as it approaches 50? Well, let's see. When I type in 50, what does it say? Error, error, error. Okay. Anyone knows why it says there's an error at 50? Why do we have an error at 50? It's an asymptote. It's because if we plug 50 in, what does it do to our denominator? It makes it equal to 0. So 50 is our limit, right? We can't have more than 50 cars going through at a time. So we can't move at a faster rate. That is our limit on our rate. Does that make sense? Okay. So it says, what happens to the length of the line? Uh-oh, it doesn't work. We get an error. Something goes wrong. So if we allow it to get up to that, then we're in trouble, right? We're like, oh no, we're now colliding, jam-packed. There's something going wrong once we hit 50. So as these people, they know that they now know a limit. They now know that, okay, Fastest amount of cars we can get through is 49 at a time. If we get any more, we're gonna cause a problem. We're gonna be moving too fast. We're gonna make some errors. Something's gonna go wrong. Does that make sense? Okay, so that's how it is a rational would be applied in a possible real world situation. Okay, so diving deeper into rationals, we're going to talk about what's called their asymptotes. What's happening when we are having that zero in the denominator, okay? So what's happening is that we are creating boundaries for our function. We're boxing it in, right? We're saying these are your limits. This is where you can go. You have 3 types of possible asymptotes. Type number 1 is your vertical asymptote. Your vertical asymptote is always going to come from your denominator. Okay, your vertical asymptote always comes from your denominator. The next 2, you're either going to have one or the other or neither, okay, which is your horizontal or an oblique. You'll never have both. You'll have one or the either or neither. Okay, a horizontal asymptote, that's going to come from the degree of your numerator and based off of the degree of your numerator and the degree of your denominator, which we're going to talk about a little bit more. And oblique also is based off of the degree of your numerator and the degree of your denominator. Notice in both of these examples, they still have a, what do you call it? Spring part. Vertical asymptote, okay? In both examples, they still have vertical asymptotes. Okay, so we're gonna look here and we're gonna talk about just being able to identify asymptotes from a graph. So looking at A, do you see my boundary lines? Okay, so where are my vertical asymptotes? There we go. At x equals -2 and at x equals +2. That's where those boundary lines exist vertically. Okay, where are my horizontal asymptotes?
The -4.
At -1. There you go. At y equals -1. So when we are vertical, we're going through the x-axis. That's why it's x equals. When we are horizontal, we're going through the y-axis, which is why it's y equals. Okay? Was that terrible? Nope, it's just reading the graph. B. What about here? Do I have an asymptote?
No.
I have no vertical, but it actually has a horizontal. 0. I have a horizontal asymptote. As you can see, both are approaching what? 0. At y equals 0. Okay. Another way that I know I have a horizontal asymptote is by looking at the degrees of my rational function. So the degree of the numerator is 1. The degree of the denominator is 2. Anytime that the numerator is less than the denominator, you're going to have a horizontal asymptote at y equals 0. Okay, that's going to be written out for you right here. Okay, so ways to know when you have vertical is easy, denominator, right? Vertical is your denominator, but to know when and if you have a horizontal and or slant asymptote. Okay, if the degree of your numerator is larger than the degree of your denominator, then there is a slant asymptote, but it's only by 1 degree. Only by 1 degree. Okay, so for example, if I have x squared over x, the degree of my numerator is 2, degree of my denominator is 1. So this tells me that I have a slant asymptote because 2 is bigger than 1 only by 1 degree. Does that make sense? Now, if I had x to the 3rd over x, this is more than 1 degree. So that means I do not have a slant asymptote. Does that make sense? I just don't have a slant or an asymptote. So this would be no slant or horizontal asymptote.
So the denominator has no number, it's not slant.
No, it's because if there's no numbers, cast with a friendly 1 is my degree. But because my degree is greater than by 1, that's why there's no slant. It's only a slant if it's by 1 degree of separation. So x squared over 1, that's only 1 degree of separation. If I have x plus 1, x squared plus 1 over 1 minus x, that's only 1 degree of separation. This is a degree of 2. This is a degree of 1. So there is a slant asymptote. Okay? If the degree of the numerator is equal to the degree of the denominator, so in this case, numerator degree equals denominator degree, you have a horizontal asymptote. Okay? However, it's based off their leading coefficients. So for example, if I have 2x plus 1 divided by 5x minus 1. Both of these have a degree of 1. So my horizontal asymptote is based off their leading coefficient. What is the leading coefficient in the numerator? 2. What is the leading coefficient in the denominator? 5. So that is my horizontal asymptote. Okay, if the degrees are equal, then all you're using is the leading coefficients. Yes. Okay, if the degree of the numerator is less than the degree of the denominator, it's only a horizontal asymptote, which equals 0. Okay, so if the numerator degree is less than the denominator degree, you're going to always be at y equals 0. Okay, this is n is greater than d, only by 1 degree, slant asymptote, n equals d, then all you're using is your leading coefficients. And if n is less than d, then it's always going to be a horizontal asymptote at y equals 0.
So what is larger than the degree of the denominator more than 1 degree?
Then there's no slant asymptote, no horizontal. It's just a vertical. No SA, no HA. As long as you have a denominator, you're going to have a vertical for the most part. Okay, so let's put it all together. We're going to identify all possible asymptotes, okay? So first, we're going to start off with, is this a horizontal or a slant situation? So my degree of my numerator is 1. The degree of my denominator is also 1. So my degrees are equal. So the degree of the numerator equals the degree of the denominator. And what does that mean in terms of slant or horizontal? It is a horizontal asymptote. So we have a horizontal. So that means y equals. And because they're the same, it's based off of their leading coefficients. My leading coefficient here is 3. My leading coefficient here is -2. Do we see that? Your leading coefficient is the coefficient with your leading variable. And your leading variable doesn't have to be in the front. Your leading variable is the variable with the highest power. Okay, so we get y equals -3 over 2 is our horizontal asymptote. And why is this again? Exactly, the degrees are equal. So the degrees are equal, therefore, all you're doing is using your leading coefficients. Okay, now we're going to talk about our vertical asymptote. Your vertical depends on your denominator. So my denominator is 1 minus 2x, and I'm going to set that equal to 0. What do I need to do to get x by itself? I'm going to subtract 1, and then what? Divide by -2. So x equals what? 1/2. So that is my vertical asymptote. So I have a vertical asymptote at x equals 1/2. Because there is a number that if I plug in, it will make my denominator equal to 0, and it is a no-go for 0 to be in the denominator. All right, let's try it again. So here, do we have a horizontal asymptote? So the degree of my numerator is 1. The degree of my denominator is 2. So n is less than d. So yes, we do. And what is it? 0. We have a horizontal asymptote at y equals 0.
Say there's 2x's on the denominator, how it's like 3x, that one's 1, and then x squared.
Your degrees are highest. It's just whatever your highest. Your degrees are highest power of your variable.
And that's the number we go to then?
Mm-hmm.
Okay.
All right, now we're gonna do our vertical asymptote. So a vertical asymptote is by setting our denominator equal to 0. If I have x squared minus 3x plus 2 equal to 0, how do we solve a quadratic? There are a couple ways. We have the quadratic formula. We also have mental factoring. We have factoring. So before you jump to quadratic, I always try mental. So I ask myself, is there anything that adds, multiplies to give me 2, but adds to give me a -3? If you set -1 and -2, winner, winner, chicken dinner. Because x minus 1 times x minus 2 is what that factors to. A negative times a negative is a positive, and a -1 plus a -2 makes a -3. So what can x not be? 1 and 2. Here are your vertical asymptotes. So we have vertical asymptotes at x equal 1 and x equals 2. Because if I plug either one of these numbers in, it would make my denominator equal to 0. If you have a degree of 2, maybe. All right, what about this guy? Do I have a horizontal? Why not?
Because it's great.
It's greater. There we go. My numerator is greater than my denominator, so I do not have no horizontal. But yes to a what? A slant. Okay, we don't have a horizontal, but we do have a slant, which we will talk about a little bit later on how to get by itself. I mean, I guess talk about now. When you have a slant, you have to do long division. That's what that automatically leads to, is long division. Okay, but it only asks us determine horizontal. And is there a horizontal? No. Next, find your vertical asymptotes. Okay, this is where it gets tricky. So x squared minus 4. Could I factor that? I can. And this is called difference of two squares. Does that ring any bells? So it factors out to be x minus 2 times x plus 2 all over x minus 2. When I factor, what do you see can happen here? This is eliminated. So what would have been a vertical asymptote? Does it exist anymore? So do I have a vertical asymptote? No. But what we do have is called a hole. There's a hole in my graph. Okay, it is a hole because I literally took a piece of my function out. Does that make sense? There's a little tiny hole. So all those factoring skills that you learn and kind of try to hone in on, that's where it comes to play. So if you're working, it's like, oh, nope, that's not an asymptote. The reason why is that you could have factored properly and eliminated the asymptote. So instead of making a whole bunch of y values not useful at an x point, is just one single point, right? Just one value that creates a hole in your graph. Okay. Does that make sense? So we have a hole. And so this function had no horizontal and no vertical. But it did lead to other discontinuities in other areas. Okay. What time do we get out of here? Oh, okay, good. Good. Now, what do you do when you're graphing rational functions? To graph rational functions, I meant to